think it's going to be offset by about 2, 3 minutes or so. Okay, there we go. All right, so we're going to go to the example. Okay, so let me make this as big, a little bigger. Okay, and let me change the size of the window, and then I'll increase the font size. Is that big enough, or do you guys want it to be even bigger? Just a tad. Okay. All right, cool. All right. So we are going to start with the C code. Okay. Oh, that's the executable. And here's the C code. All right. So what is interesting about this program that we did not talk about on last Thursday would be the use of a pointer as a member of the structure, which is really just a combination of pointers versus, a member. But, we're going to talk about it. So lines 3 to 7, that is the structure definition. Member N, which stands for next, is a pointer to a struct X. And if you're thinking, how can you use struct X, as the type of a member, and we are inside the definition of struct X? Well, the key here is N is not a struct X. It is a pointer to a struct X. And every pointer in every single platform has a fixed size. So in this case, this is a 64-bit pointer, but in the case of TTP ASM, it is 8-bit. Okay, so we don't have a problem with how this is going to be defined. So what may be a little bit harder to understand is from line 9 to line 13. I am defining a global variable, that is an array of struct x's. Okay, so there are, in this case, 3 members or 3 elements in the array. The first element of array R is going to have the first member, which is n, being the address of the next element. And then v is 20, and then s is 0. For the second element, or I should say element 1 of the array, member n is the address of the third element in the array. V is 11, and then S, which stands for sum, is 0. And then for the last one, for the third member or excuse me, element 2, okay, which is the third element, the pointer for member n is null, and then V is 9, and then the sum itself is a 0. So do we have any questions about a initialized global variable that turns out to be an array of structures? No questions? No questions? All right, cool. All right, so now we look into main. This program is actually a bit more complicated than your actual homework assignment. So I thought, it's okay. We can talk about this. So this is your main, and it is the only function in the entire program. We have ptr pointer as a struct x pointer, or the address of a struct x. We have pointer stack, which is an array of struct x pointers. And then we have pointer sp, which is pointer stack pointer. Yes, we have a stack pointer to a stack of pointers. It is a double pointer to a struct x. Okay, in other words, the variable called ptrsp is a pointer to a struct x. Are we doing okay so far? All right. And then the program starts on line 20. It is just initializing a bunch of stuff. So PTR is initialized to ARR, which is the beginning of the array. Pointer stack pointer SP is pointing to the beginning of pointer stack, which is here. And then this is the first loop, this is the second loop, and there are certain things that look somewhat hairy here. Okay, so I'm going to explain, what each line is doing. On line 23, we are essentially so the direction of how this stack operates is opposite to what we are used to. So we are basically pushing PTR on the stack, and PTR has to be non-null to be in the body of the loop. And then what we do is we increment oh, excuse me, not increment. We look at the n member of the structure, the PTR the pointer is pointing to, and then whatever that turns out to be, we use it to update pointer until we encounter the null pointer, then we exit the first loop. The second loop is only looking at pointer stack pointer. So it is going backwards. We are basically popping in the second loop. Yes. So n is a member of struct x in this case, and it is a pointer to a struct x. So we can take a look at the definition of struct x. So member itself is a pointer to a struct x. Yep. No, this one is not a tree. This one is strictly a it's strictly a linked list. So the initialized array already has all the pointers already initialized. So we are not constructing the linked list by hand. It is already constructed. We're simply following the linked list in order to add up all the values, but we're adding the values to the sum of each structure, in the array. Yep. All right, so we can run this code in C. Okay, this program does run in C. So if, in case you want to understand how this works, you can always use GDB to help you understand how this works. Um, so do we have any additional questions about the C code before we run it? Yes. Line 9 to 13. That's for the initialization of the array, so that we have a linked list to begin with. So basically, the first element or element 0 points to the second element points to the third element. The third element has a null pointer, so it terminates the linked list. But for the most part, you do not need to understand data structure to translate the code, because people may complain and go like, but CISP 440 is not 430, sorry, is not a prerequisite of this class. Well, that is true. But I'm not asking you to write the C code. I'm asking you to translate the C code into assembly code. So there's a difference between those two. Yes. Third one is the sum. Yeah. Mm-hmm. Yes. Yep. That is correct. Yep. Mm-hmm. Huh? The sum is used in the second loop. So when you look at the second loop, this is how sum is utilized. So it is the value of the node itself plus the sum of all the sum of the values of all the following um, nodes. So it will first check to see if there is a next one. If there is a next one, then it will look at the sum that is recorded by the next node. So it's kind of recursively defined, but for this class, all we need to do is to figure out how to do the code, not so much the algorithm itself. So go ahead. Yeah, the sum is going to be initialized, later on. So I could have just, stashed some really random values here. It would not affect the algorithm, because the algorithm would actually put correct values into the sum regardless of the initial value. All right. So yeah, so this program is intentionally kind of more difficult compared to your homework assignment, which is due in a week. But I thought that, hey, if we start with something more difficult, you guys can have a easier time to kind of reapply the techniques to the program that you're supposed to write. Yep. Question? Nope, it won't be always zero. So the best way to track down what this program is going to do is to use GDB. So that may be part of the things that you want to do during the lab today, because the actual lab today is fairly short. There are only like 3 questions, and then there's the programming part of it. So that means, when you're at the lab, you will have a computer in front of you. I know many of you bring your own devices here, but not everybody has a computer right now, so I can't really rely on that. But once we get to the lab, you're encouraged to use GDB to kind of figure out how this code works, which probably involves single line, tracing the program and see, how the values are changing. And also you can use it to track down, what happened to all the other nodes, because you can use GDB to print R itself, and it will print all 3 elements at the same time. So it really saves you a lot of time when you print out the entire array, because you get to see all 3 elements as structures broken up into their members when you do a print R. I'll show you, just how to do that. Okay, just so that when you get to the lab, it's easier for you to kind of conduct your own experiment. So we do a list. Okay, put a breakpoint on line 30. So I'll just do a really quick run. Run all the way to line 30 and then print R itself. So what we see here is the entire array. The last item would only have the value being initialized to the sum. The second to the last item is going to have its own value added to the sum of the next item. So 11 plus 9 is 20. That becomes its own sum. And then for the first item, it is the same deal. Um, Basically, we have its own value is 20, but so we add its own value to the sum of the next node, which will give us a total of 40, and that 40 is stored as its own sum. So are we seeing the relationship between the nodes in terms of the value versus the sum? Okay, okay. All right. So shall we move on to the assembly implementation, or do we have more questions about the C code? Okay. Looks like we are ready to move on to the assembly language implementation. So we'll go ahead and do just that. Okay, quit. And then we'll do the typical thing, which is looking at the sample code on the C code on the left-hand side, and then the assembly code on the right-hand side. All right. Okay. First thing first, we are going to have the entry code, which is typically the same for all the programs that we write now. So we have LDI E0, which is not really needed. Then we have decrement LDI A dot 6 plus, decrement D, STDA, JMPI to main, and then when we come back, we just halt. In other words, main is no different from a regular function. Um, and then we define our structure over here. So we have x underscore n being the first member, and then we have what is it? V being the next member. So it's x underscore n 1 plus, because n as a pointer only takes up 1 byte with the architecture, with the TTP architecture. And then x underscore s, the sum is x underscore v 1 plus, because v is an unsigned 8-bit integer. And then we have x underscore size, which is x underscore s, the offset to the last element, plus the size of the last element, which is also just 1 byte. So now we have the structure defined. We now can define R as a global variable. So in assembly, you really do not have structure. So there's nothing equivalent to the curly braces. So what you need to do is really just to kind of use a bunch of bytes to do this. So I'm going to use this Let's see, is it 2? Yep, I think so. 20 byte 0 byte dot 2 plus. This one is 11 byte 0 byte dot 2 plus. I think it's supposed to be dot 3, so I think I got this wrong, but it's I'll fix that in just a moment. Okay. I think these are supposed to be 3, not 2. And let's see, we have, oh, okay. So this one is supposed to be just a 0. There we go. All right. Yep. So byte itself as a directive is telling the assembler whatever the expression on the right-hand side of byte evaluates to, reserve one byte along, in the memory space and initialize that location to whatever that value turns out to be. Okay, so if we specify dot 20 in decimal, it will reserve a byte and initialize that byte to 14 in hexadecimal because 14 in hexadecimal represents 20 in base 10, or in binary it would be what 00. Okay, it's going to be 1 0001 0 oh 0001100. Okay, there we go. Okay, I have to do the conversion in my head. The dot has the same meaning as the dot as always, which is the current location, and then it is in reverse Polish notation. So 3 plus means just add 3 to the current location, which turns out to be the location of the next structure. Yep. So that's how it works. All right. So when you write your code in your homework assignment, you obviously probably do not want to write everything, at the same time. You probably want to put some halt instructions around the code just so that you can get to a certain point and then you just figure out, okay, what is in memory right now? Okay, what does it look like? The assembler will tell you everything that is statically determined. So the assembler itself can be helpful, but if you want to know what is happening on the stack by the time you get to function f, which is what you need to write in the homework assignment, then you can also put a halt instruction right at the label of f colon. So this way, the program stops as soon as it gets into the quote unquote gets into the function, and then you can get an idea of what the stack looks like, which I think is super duper important because that's the first thing you need to verify is do you have a good understanding of what the stack looks like and what should be where on the stack. All right, so that's done. We now go to main, and main has a bunch of local variables, so we're going to have to. I personally like to use these constructs to remind myself where I can find each one. But whether you want to do the same thing, it's up to you. So this is main pointer 1 plus, because pointer itself is only going to take up 1 byte. So where I can find the next local variable is just 1 byte away from where I can find pointer, which is PTR. Hmm? Uh, it serves the same purpose as all the labels that we have been using, which is the offset from where it is the offset from the base of the call frame to where I can find the local variable called pointer. Yep, yep. I'm just borrowing all the same names as the C code. Now, this one is going to be a little bit more interesting. Okay, so I keep the same name. Okay, so this way it's easier to look at the connection between the C code and the assembly code. So this one is a little bit more interesting because pointer stack is not going to be just 1 byte. It is going to be 3 bytes. Okay, but to be exact, this is what I need to specify because it has 3 elements. Each element being a pointer only takes up 1 byte. So the multiplication of 3 times 1 tells me the total number of bytes that the pointer stack has. And then we have to add the 3 to pointer stack where we can find pointer stack in order to calculate where we can find pointer stack pointer. Okay, so a picture is going to be super helpful, and that's also partially why I set up today's lecture using my super note, and it has, I forgot to turn on the screen share first. So, just refresh or reload, it should do it. Give me a second here. There we go. Excellent. All right. So what we have here is, okay, so I typically draw memory space where, this is high memory space and this is low memory space, okay? So what we have here is the first item is PTR, okay, pointer. The second item is pointer stack, so PTR stack. But PTR stack, pointer stack has three elements in it. So this is the first element, takes up 1 byte because it's just a pointer. This is the second element. This is the third element, also takes up 1 byte. So by the time we want to allocate for pointer stack pointer, it is already here. So if you look at how the labels are defined, this is just 0 because it's a constant of 0. This is 1. This is 2, 3, and this is actually 4. If you look at the offset from where the base of the frame is, this is the base of the frame. All right. So based on this, we are missing one item from the frame, which is the return address. The return address is always here because it is pushed by the caller, whereas the local variables are allocated by the callee. So that's why this portion is allocated by the callee as opposed to this portion, which is pushed by the caller. Do we have any questions about this picture? Yep. Because I want to emphasize that we have three elements, and then each element takes up 1 byte. Yeah, that is correct. Yep. Yep. Go ahead. Mm-hmm. Mm-hmm. Which space? Below or after? Below or above? Because that's pointer itself. This space is used by pointer. This is pointer stack 0. This is pointer stack 1. This is pointer stack 3. And this is pointer stack pointer, which is just a single byte because it is just a pointer. It's a pointer to a pointer, but any pointer only takes up 1 byte. And then above that is our return address. All right. Yep. Mm-hmm. Nope, because nothing here is actually a struct X. They're all pointers. Even the array is an array of pointers. So nothing here is going to use X underscore size because they are not structures. No local variable of main is a structure. So if I go back to the source code, even in the C code, you can see that they all have at least one asterisk, which means in TTP they only take up 1 byte. That is correct. All right. And so in usual tag manner, I use LVS to keep track of local variable size, right? So it is the offset to the very last one plus the size of the last one. So even though pointer stack pointer is a pointer to a pointer, but it is a pointer, so it only takes up 1 byte. That is the reason why we have this one here. So with this all done, we can, yes, can you speak up a little bit? Okay. So it's just my convention to use the function name underscore and then the name of the local variable. So this way, if the C code has the same name for multiple functions as a local variable, I don't have a problem, in the assembly code. All right, so now we just need the usual entry code, which is LDIB with the number of bytes that we need to reserve. Okay, so subtract that much from the stack pointer, and then later on we have to deallocate. So by adding this to the stack pointer, we are deallocating, and then we can use the usual um, return code, retrieve the return address, deallocate it from the stack, and then continue execution at the return address. So that's fairly typical stuff. And then we use LDIA 0, even though the return value is not used, but since the C code does specify that, eh, okay, we'll do that. All right. So now the difficult stuff is, how do we implement everything from line 20 to line 29? Yes. Nope, the local variables are reserved by the time we get to line 34 because of lines 31 and 32. The stack pointer would have adjusted itself to point to the base of the frame by that time. Okay, go ahead. I is actually not used in the C code, so we can probably just delete I from here. But but you're correct. Okay, there's one local variable that I planned to use initially, and then later on decided not to use it. Yep, very good point. All right. Any other questions? Okay. All right. So we'll focus on line 19. So something like this, should be fairly kind of run of the mill at this point. So we get to the offset of, okay, R is a little different. So R is really just the label itself because it's a global variable. It's not on the stack. So if something is not on the stack, it does not make sense to add the stack pointer to whatever that label turns out to be. So R is just R, okay? So now we just have to figure out the left-hand side, which is pointer. So we have B main pointer add BD STBA. So now we are done with line 19 of the C code. And now we move on to the next line, which is LDIA PTR stack um, add AD. That would be the address already. Okay. And then we store that to the left-hand side, which is LDIB pointer stack pointer, or I forgot about main. There we go. There we go. All right. Add BD. So now B has the address of pointer stack pointer, and now we can do the store like so. There we go. All right. When you are writing your code, I would strongly suggest that you debug the code along the way and don't just write the entire program before you start to debug it. So now would be a good point to debug the program. The way we debug this program is first we need to have a good understanding of what is where on the stack. So now in typical fashion, we look at all the locations and then we say, okay, what is supposed to be at location FF? That's the return address back to the entry code. Okay. And then we look at the locations below that. So there'll be FE, FD, FC, FB, and one more, which is FA. All right, so we'll start at the lowest location. That is where pointer is. This one is going to be pointer PTR stack, the first element. And then I'm just going to be pasting this and here. Okay, because these two are the second and the third element. So we are just changing the index here. And then the last one is PTRSP. PTRSP is supposed to be here. Okay. So I hope you guys can associate the comment here with what I drew earlier on the tablet. So we're good with that, associating the picture with the comments. Okay. So now, after these two lines of initialization, we need pointer PTR to point to the actual label R, which I do not know where it is now. The assembler can tell me that. Um, Pointer stack or the content of pointer stack has not been modified, so they should all be zeros. And then PTRSP or pointer to a pointer stack pointer should be at FB because that is the beginning of the pointer stack array itself, which is what line 20 is supposed to do in the C code. So are we good so far? All right. And at this point, the stack pointer should also point to location FA because it is the last thing that we allocate. So the stack pointer should point here. So from your perspective, it is probably a good idea to say, okay, I'm not really sure whether the program is working up to this point. Put a halt here. In other words, we don't even bother to finish main. We just want to see if what I thought should be on the stack is in fact on the stack. Yes. hmm because in the C code we have a return zero. Okay. Yep. But this has been what I do for several days already. No, it does not. But at least the C code is consistent with the assembly code. That's what I'm aiming for. Consistency. Register A specifies the return value. hmm All right, so what we'll do is make sure I save this file because a lot of times I forget to save the file and then I try to run something and then it doesn't work. So we'll go ahead and I can cancel this. Go to my um oh okay, forgot about the slash. There we go. CSP 310 reverse spider. So we're gonna turn in example.ttp-asm. All right. Yep. Well, we'll see in the trace. That's why we can trace it because this way you can associate the assembly code with what is actually happening when the program runs. So we'll take a look. I'll specifically try to address your question when we get to the browser, which I think is this one. Assembler is right here. There we go. All right, so to address your question, okay, so we can see how the code executes. No op doesn't do a single thing. Register D starts with a value of 0 anyway. Blah blah blah. So all of this is kind of things that we already know. But now we can see how the return address to the entry code is stored on the stack. And then when we proceed any further, this instruction, which is the one that you were asking about, is loading 5 into register B, and we already know that there should be 5 bytes reserved. And then the next instruction subtracts 5 from the stack pointer. So now the stack pointer points to location FA, which is consistent with both the diagram here, okay, and also the comment in the C code and right here. Nope, not this, not this one. Oh, this is actually a homework assignment. So let me go back here. So it is consistent with this diagram. So does that explain, how we allocated space for the local variables? Yep, yep, that is exactly it. All right, so I will give you guys a few suggestions. Okay, once again, it is up to you to choose what you want to do. Um, for all the previous programs, okay, if you have not done so, please comment those programs. I gave all the programs to you for a reason so that you can comment those programs. After you comment the programs, use River Spider to run it again. Okay? The reason why I make that suggestion is because if you do that, then by the time you get to the trace, not only do you see the instruction itself, not only do you actually see the instruction and also the end result of the instruction, but you will also be able to see your own comments, which means you can follow along with your own description of what each instruction is supposed to do in the actual execution of the program. Okay, I think personally, I think this is the most useful tool to help you understand what is happening with the instructions. Yes, it gave you errors. Okay, we'll try that. Okay, I think it will give you a problem if you have a tab character, but if you don't use tab, I think it should work. Okay, so we'll just say, take a break here. Okay, save the code, and then try to run it again. Uh, there we go. Because I think it should work. I mean, I'm almost 100% sure it should work, but hmm? Yeah, I think see, right here, it, the comment is preserved in the analysis tab. But make sure you don't have any tab characters. Okay, you can always configure your editor not to use a actual tab character, and just use spaces. Yeah, yeah. But most editors can be configured not to use the tab character. All right. Any other questions? Shall we continue? Yes. You mean in the C code? It is a stack pointer of the pointer stack. If you look at this array as a stack, this is a stack pointer of that stack. But it's not that part actually is not important. R is initialized. Oh, okay. In the C code, right here. Yep. Yep. There we go. All right. Cool. All right. So we're gonna continue. So we are done with line 19 and 20. So now we are on to line 21. So line 21 is the beginning of a loop. So we go while zero begin. Well, because this time it's not the only while loop. So the while zero versus the while one is going to be handy. If you have a begin, you probably need an end. At the end of each loop, right before, you need an unconditional branch back to the beginning. So I can do all this just knowing that we have a while loop, because every while loop needs these three elements. So now with all these done, I can go back and say, okay, how do we exit the loop then? Because now we have a tight infinite loop. I just need to specify the logic to get out of the loop now. LDI main pointer add AD LDAA and AA JZI to while zero end. So that means when pointer PTR is null or zero, we exit the loop. All right, so now we can go to the middle part of the loop, which is line 22 and line 23. Line 22 on the right-hand side is pretty easy, so we'll do that first. So now we have LDI. Well, we actually don't need to do a single thing because register A still has um, pointer in it. Okay, because we just checked it, right? So it is still in register A by the time we get here. So if you want to like not do anything, but also want that to be quote unquote self-documenting in the trace, you can do something like this. Okay, you can say register A still has PTR. Okay, you can do something like that. Or personally, I would abbreviate it. So I'm just going to say register A is PTR. That's how I would document it. But how you want to document the code is entirely up to you. So I will sprinkle and leave behind a little bit of commenting, but you really need to download this whole thing and comment the whole thing using your own annotation. And remember, the final exam is always open book and open notes. So I would definitely bring the opcode table unless you feel confident that you have remembered all the instructions. And I would also bring all the commented version of the code that I have gone through in class. If you know someone who took this class before, you can take their programs and bring it along with you too. Just remember, the more stuff you bring, the harder it is to find the one thing that you need to find. So I would kind of keep that in consideration as well. Okay, so it's not always bringing more is better. All right, so now we move on and go like, okay, what about the left-hand side of this thing? It looks kind of ugly. So post increment means the increment happens after the store. Okay, after the entire line is done, we have the increment. So I'm not going to worry about the incrementing until I got everything else done. Okay, so now we just have to go like, okay, well, no, regardless of what we're going to do, um, we are going to have to get to pointer SP, right? Pointer stack pointer. So we're going to do, we cannot use register A anymore because register A represents the right-hand side of the assignment. So I'm going to start with register B and PTR SP add BD. That is the address of PTRSP, which I think I want to preserve as much as I can because the auto increment is applying to the local variable itself. We are not incrementing whatever it points to, we're incrementing the local variable. And I have the address in B right now. So that means I might want to save it, okay? Because I have one more register to play with. I might be able to get away with this. But nonetheless, this is just the address, which is not the value of PTRSP, which I need in order to do this dereference. So I'm going to do LDCB. So the register C is the actual value of the local variable, which turns out to be a pointer to a pointer. And now I can store to um, whatever C is pointing to, because this assignment is storing to whatever PTR-SP is actually pointing to. The post increment, as I said, you can ignore it for now. So now we store the right-hand side to whatever the left-hand side specifies. So that means everything is done except for the auto increment. So now we can do the actual increment of whatever C has, because C is the value of pointer stack pointer, and then we store that back to whatever B is pointing to, because B is the address of pointer stack pointer. So there we go. I have not tried this. You can give it a try, which is to download the transcript of the actual lecture. There's a plugin for Chrome to just do that, okay, which is super handy. And then you download this code, which I'll give you in the announcement, just as usual. And then you upload both to ChatGPT and ask, hey, ChatGPT, can you use the lecture recording caption to help me document this code? I'm not sure whether that will work or not. I'll be I'll be really surprised if it can work perfectly because the line number changes as we add more code. So it may or may not be able to do it, but it'll be kind of an interesting experiment. If ChatGPT can do that reliably using the correct line number, if I were you, I would be very scared. I would be very concerned about how I can get a job. Yes. Uh-huh. No, this is just the beginning of the array. Pointer points to the very beginning of the entire array. and that's all it is. Yep. 21 to 24. It's different because I'm trying to keep track of all the addresses of the elements of the array because R is not an array of addresses. R is an actual array of structures. Every element of R is a struct X, as opposed to uh, pointer stack, which case every element of that array is just a pointer. Okay. So now we are going to implement line 23. Okay, so by the time we get to line 23, register A still has pointer in it because we don't have any code in between to modify register A. So nothing from line 52 to line 57 is changing register A. We use it, we reference it, but we're not changing it. So that means if I want to do some commenting here, I can go like, oh, okay, no op, A is still 20, is still pointer, which is handy because that saves me a little bit of time, not a whole lot, but just a little bit. Okay, so now we need to handle the right hand side, which is give me the value of member and of the structure that pointer is pointing to. Once again, it is important to describe the expression with precision because when you describe an expression with precision, the description itself will tell you the ordering or the dependency of how what needs to be done, and also it will give you an idea of what needs to be done. Okay, so that's my take on why we need to be precise when we describe what an expression does. All right, so to do that, we are going to load the offset to member n from the beginning of a structure into a separate register. Register B is good. So that would be x underscore n right there. That's the offset to find member n from the beginning of a struct x. And then we just add BA, just in case I need pointer back for something. I don't think I would need it back for anything, but that's okay. So at this point, we have the address of member n of the structure that is pointed to by pointer stored in register B. And then what we'll do is to retrieve it, okay? So we have to use the LDBB to retrieve the actual value of member n of the structure that is pointed to by pointer, okay? And then we can store that to pointer itself. Register A does not have the address of pointer, so I have to recalculate the actual address of pointer. So now we have to do the typical thing. I can now reuse register A, by the way, because register A had the value of pointer, but I need to get to the address of pointer, so I have to kind of redo the whole calculation, which is not too bad, just like that. And then we do a store like that from register B, and that should do it. Okay. So that concludes the body of the loop, and then the next statement should be the unconditional branch back to the beginning of the loop, which means this may be a good time for us to kind of stop the execution of the whole program and to check whether it works or not. Okay, it's not to finish the loop and just do it. Put a halt instruction right after line 65. Yes. Mm, register A is pointer, but we are overwriting pointer because so in order to overwrite pointer, I don't need the value of pointer, I need the address of pointer. That is correct. Yep. Okay. So we'll put a halt instruction here and take a break, okay, which we are not going to do um, because I need to finish this program today and yeah, I think we can do it. All right. So at this point, what do we expect to be on the stack? Okay, that's kind of the question because in order to debug the program, you kind of need to know, you know, what it is supposed to do. So that means, right now at this point, there are a few things. Okay, so we have PTRSP. um, whatever it points to, which is location FB, should get pointer, which is whatever is in R. So that means, this location should also be just R, which is the beginning of the array of struct X. Okay, so that's the effect of line 22. But we are also auto incrementing pointer SP, or pointer stack pointer, which means this should be incremented to FC. And then we are changing we're changing pointer to be whatever it is pointing to next. So pointer should no longer pointing to R, which is the beginning, or also it used to be it it is the same thing as this, right? This was basically what it had. So now it should point to whatever is next to the first element. So it should be this. All right. So that's kind of what I think it should do. And I put a halt instruction at the end or right before the unconditional branch of the loop, which means, I should be able to see exactly just this. All right, so that's what we're going to do. And this part is actually very important because I'm trying to show you guys how to debug a program and how to write your program step by step. Okay, not to do the whole thing, but do it in smaller steps, know what that smaller step is supposed to do, and then double check, verify before you move on. Yes. Um, I cannot remember, but we'll check. Control G will tell me. Ah, you're right. Forgot. But it is always good to have a favorite mistake to make because that's your go-to. It's like, okay, did I do that? Yep. Thank you. So let's go back to the trace itself and see if that is what happened, right? So now we look at, okay, let's see what is supposed to be changed, and that's already documented in the assembly code. Okay, so I think the first one we can check is the change to whatever SP is pointing to, which is location FB. That's going to be the first change that we can observe. So FB should be R. So now we go here. The first thing we need to do is to go back here in the Assemble tab to figure out where R is. So R is location 0A, okay? And now we go back to the analysis and we go like, okay, according to what we expect the program to do, location FB should now be 0.8. Okay, so let me just kind of put it here as well. Okay, so that's what we are looking for. So keep scrolling down from where we were last time. Aha! Okay, so that is good. And we also want to now look at the other locations. This is supposed to be FC. It is FC, okay, so that's all good. So you don't have to do a line by line or instruction by instruction check as long as the landmarks are all working out, okay? And I would say writing to memory is the typical landmark that I would look for, but you can have a different strategy if you want to kind of look at something else as a landmark. And FA is getting FD, okay? So let's see, this is FA and it is getting the address of R1. So R1 is R0 plus 3. So that would be 0A plus 3. So 0D is indeed correct. So far, so good. Okay. So now, with all this verified, I can go back to the program and go like, okay, cool. So now we can take out the halt instruction, let the loop finish what it's supposed to do, and we can now, start with the second loop. Are we doing okay so far? Okay. So what you probably want to write down is, how to approach the problem. Not so much, the actual instructions here, but how to approach the problem. Okay. What concepts are involved and what they entail. And also having a short catalog of, what time, I start to talk about which topic or what I talk about at that time. That can be helpful as well if you want to use the recording to help you go like, okay, let me go back to that time when tech talks about blah blah blah, so that I know how to document the assembly code. All right. So now we continue with the next loop. The next loop is while one, okay, because these two loops are sequential. So one is zero and the other one is just one. And typical, we have begin, we have end, and then we have an unconditional branch back to the beginning, okay, like so. And now we have to figure out, okay, how do we get out of the loop? To get out of the loop, we are checking to see pointer SP is the same as pointer stack or not. If it is, we get out of loop. So that means we have to compare those two, put each one into a register, and then do a CMP. This time there's no shortcut to use AND AA or AND the register and itself. All right, so we'll do the whole thing. So now we have main pointer, stack pointer, add, oh, okay, forgot about the register, add AD. But PTRSP itself is a pointer, is a local variable. So to get to the value, we kind of need one extra step. And I'm trying to save register A for now because I know I need it back later on. So that's what we'll do. And then what we do is we need to get to pointer stack. So now we do LDIC with main pointer stack. But because pointer stack is an array, you cannot compare an array to just a single pointer. So what we are really comparing is the address of the array. Okay, we are not even bothering to get into the elements of the array. We are only referring to the address of the array. So by adding CD, we have the address of the array. So now all we need to do is to compare register B and register C. So CMP BC. If they are the same, we need to get out because the loop says if they're different, we stay in the loop. So if they are the same, we're going to get out, which is going to while one end, like so. So now this part here is the body of the loop. Are we good so far? Okay. Now, if you're thinking that, okay, Tech is going through this code a little bit too fast, well, the whole idea is I'm recording it. Okay. And the recording includes my description of what each instruction is doing and how it relates to the C code. So that means, that is how what you can do is to kind of listen to the lecture again at a slower rate and you'll just kind of pause and then go like, okay, do I, and not to just translate what I said, okay, not to just transcribe what I said, but actually understand what I said before you comment the assembly code with your own words. All right, so now we need to decrement. Okay, good thing I saved register A and B. Register A has the address of pointer stack pointer, and then register B has the current value of pointer stack pointer. So now I can decrement the value, which is in register B, and then store that back into whatever register A points to, because register A still has the address of pointer stack pointer. Okay, are we still doing okay so far? All right. So now we move on to line 27, which is, ooh, lots of parentheses and looks kind of hairy. So when you see something like this, one thing you can do is to draw a picture of what needs to be done here from the perspective of a syntax tree. And then you do you basically work your way from the bottom up, when you look at a syntax tree like that. Does everybody understand what I mean when I said a syntax tree? Okay, so let me go ahead and do this here. So at the top level, we have an assignment. And I know because I need to do this on the tablet first, and then I'll show you the actual code here. On the right hand side of the assignment, okay, we got a whole bunch of stuff to do. But of that whole bunch of stuff to do, what was the last one? Nope, 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 nope. The plus. Okay. So it's adding something we kind of know how to do. So it's the right hand side that is a little bit hairy. So when you look at the right hand side of the addition, what kind of an operation is that? Yep, it is a ternary expression, which means it has three parts. We have the conditioned, we have the then, we have the else. Okay. And of those three, the condition itself is not particularly difficult. Well, I guess it is because it's asking is member n of the structure that is pointed to by the pointer, which in return is pointed to by pointer sp, is it null? Is it null or not? If it is not null, then we do this, okay, which is accessing the sum of the structure that is pointed to by member n of the structure that is pointed to by a pointer that in return is pointed to by PTRSP. Okay, so I did say that in a correct order. Okay, it took me a little bit of time to process that in my head first, but that's kind of what it is. Okay, but when you can spell out an expression like that, it's already telling you what you need to do. Okay, the rest is kind of a little bit tedious, but not super duper difficult. And then the other one is just a zero here. So I'm just going to show you the syntax tree that I have drawn so far, which is very simple, okay, because I wasn't trying to capture everything. I was just trying to capture enough to kind of show you what you need to do, okay? So the first thing we need to do is to evaluate a condition here, okay, which is the condition that goes here. So this is what we need to do, step one. And then we have to kind of work on step two, step three over here, just so that we can finish the ternary expression. And then this will be number four, okay? Because until I have four and this particular value here, I cannot calculate the plus. So this would be number five. And then we have to calculate the address on the left-hand side so that we can finish the actual assignment operation. Is that making sense? Okay, so you can do the same thing. Okay, it's not. I know this is not a compiler class, but to look at an expression and turn it into a structure like this, I think most you guys can do it. Can Is that okay? All right, all right. So knowing that this is what we need to do, now we switch back to the code and then start this rather long journey of doing exactly that. So the first thing is to figure out this entire thing. Because I have, I need to rely on whatever pointer SP points to, at least again. I will try to save that into a register because I need it here as well. So that means, the first thing I do is to do the LDIA with, oh, I have that already. I don't have to do a calculation. Okay, no op, okay, to represent that. There's no need to do this because I got it already because I just decremented it and put it in back into itself. So register B is whatever. No, I take it back. Register B is pointer SP, which is good. It's at least close to what we need because it's not what it points to. So that means to get to what it points to is just another LD instruction. So LDBB. So now register B is whatever pointer SP points to, which means every time you see something like this, just say register B. Is that okay? All right. Now, when we run the code, we can actually double check if that is the case. Okay. So why don't we just do it? Okay. So every time you suspect that you got the right implementation, I just figure out how to do this, put a halt instruction. Figure out whether the program is doing what it is supposed to at this point. So what we now need to do is to kind of complete the whole picture of what the stack should look like. Okay, so this one is going to be D, and this is going to be another three added to it, which is what is D, and then E, F, and then 0, 1, 0. That's right. Okay. Let me see. Yep. Okay. 13 plus 3 is 16. 16 is 1 0 in hexadecimal. So that is what it is supposed to be. And then the stack pointer would point to one location past FD, which is FE, which is itself. Okay, it does point to itself, and then the first thing we do is we subtract it. We decrement it, so that means it turns back into FD. And then at this point, I need to take a look at the code of what we have done so far. Okay, so we want to know at the no op instruction whether B is pointer SP, which is supposed to be FD. And then after that, we want to know whether register B is what is at FD because we dereference it. So what is at FD is 10. So when we get to the halt instruction, register B should be 10 in hexadecimal. Are we doing okay so far with this kind of explanation? Because you cannot test or debug your code program before you know what is supposed to be stored in memory, or at least in the registers. So we save this, and then we just run it. Okay, hopefully I did not make a stupid syntax error, but it happens from time to time. All right, so it does run. So we now go back to the uh, analysis like so. And then we just look through all the memory write operations and see if that is what we see. Okay, FC gets FD. This is the loop, right? By the way, this is where the loop is, what the loop is doing. Location FA stores 10. I think that is consistent with what we said it would do. FE becomes a pointer to itself, and then it decrements later back to FD. FA gets 00. Okay, so that was not accounted for. So I need to take a look at what I commented here. Nope, uh, this one. So FA is the pointer. Oh, it does get back to 00 because it gets the next of the last element of the array, which is 00. So that is actually correct. So this one does get back to 00 at this point. So every time I see something that I'm suspicious of, like why is it like this? I did not anticipate it. I have to look into it. Okay, so do not let something that you do not expect to kind of slip by. You always want to explain those. Sometimes it's not because of an error. Sometimes it's just, oh, okay, I forgot the program is supposed to do that, which is the case in this case here. All right, so FE gets FE. Oh, we were there already. And then we see how it's supposed to decrement back to FD. So that is consistent with our, um, and then B is 10. So everything is as expected at this point. Okay, so now we can go back and continue with the coding. If you know how to use GitHub or get the command line program or something like that, it'll be a good idea to check in your code. Once you check something and it works up to a certain point, check into the repository. So in case you do something later on and the whole program doesn't work anymore, including the parts that used to work, at least you have a place to retrieve an earlier version to revert back to, oh, okay, this is the last known good state of the program, and I can at least restart from that point. So I highly recommend, getting something like that, or just use GitHub. All right. So now where are we? Right. Okay. So we got this. Okay. So the first thing we need to do is to evaluate the ternary expression, which is accessing member end of the structure that is pointed to by register B at this point. So to do that, we load into some register A or C the offset to member N, add AB because I don't want to destroy B. B is useful to me. So I want to preserve B as much as I can. So now register A has the address of member N of the structure that register B points to. Okay. And what do I do with it? I just need to know whether the value is null or not. So I have the address at this point. So now I get the value of that thing, and then I can check whether it is null or not. Okay. And if it is null, we go to the else case. So this is going to be the else case of a if then else structure inside while one. So this is how I would name it. Okay, which means if I continue here, this is the then case, and then I define and then branch around the else case. Okay, JMPI around the else case, go to end if zero, and then we have the label while one else zero to be defined here, which is corresponding to the else case. The else case, and then also the end if is going to be here. While one and if zero goes here. This one is corresponding to the zero, which is really easy to do. And I just have to choose the register that is supposed to store the result of the entire thing. Register A is okay, we can do that. Okay, so we'll just use register A. So now we go back to the then case, which is the really kind of hairy one. And I think of the entire program, this may be the hairiest portion of the entire thing. Okay, but we do it one step at a time. First thing is to um, kind of spell it out in a really precise way. We are trying to access member S of the structure that is pointed to by member N of the structure that is pointed to by register B. Okay, so since we already have this figured out, okay, the reference pointer SP is already figured out, so it's pretty easy to get to member N of the structure that it points to. So that's the first thing we need to do. All right, so let's do that. So we just have to do LDI. We still have register B preserved, so we're going to reuse register A for whatever we need to do. So this is going to be member N. Well, member N is already, yeah, member N is already in register A. Cool. So we just say no op A is, okay, and I'm just going to repeat the whole thing, okay? Yeah. So because A is already that expression, so now we just have to worry about accessing member S of the structure that register A is pointing to. So I cannot mess up register A or register B. So register C is ready. So X underscore S add CA. Okay. So that would be the address of member S of the structure that register A is pointing to. And because we are accessing the value, so now we need to do a dereference, LDCC, and to be consistent with the stuff that we were talking about using register A to store the value. So I'm going to put it back into register A just to be consistent, so that by the time we get to while one and if zero, register A has the value of the entire ternary expression. So now we can continue at that point. So the lecture is going to last a little bit longer today because I kind of want to finish this whole thing before you guys go to the lab. As I said, the lab only has 3 questions, so it's not going to take you a long time. This is more important. So we're going to finish this program. So by the time we get out of this, we already have everything in here. So this entire expression is evaluated. Now we just have to get back to this one. And at this point, we still have register B pointing to register B is still the same thing as what it used to be, which is PTRSP dereferenced. So that means, okay, accessing member V of the structure that it points to. We know how to do that. So LDI A with X underscore V add AB. Um, we okay, you're right. Okay, so we need C. No, we cannot use B because we still need B on this side. We can use register C. So add C B. Okay, there we go. So register C is now the address of this entire thing. We need to dereference it once. So LDCC. So now we can add those two. And let's see, register A. We don't need register A anymore. Okay, after this instruction. So add AC is going to work okay because register A is now the entire right-hand side of this expression. and then we just have to calculate the address specified by the left-hand side. So this part is already done. Okay, whatever pointer SP the reference to is already done. It is still in register B. So now we just have to say, okay, where do we find member S of that thing? So LDI register C can now be reused. So we'll use that. X underscore S add to B. So now register C is the address of the entire left-hand side, which means we are now ready to store to that location with whatever is on the right-hand side, which is in register A. So that is what it is supposed to do. This is a lot of instructions, okay? So it is time to put a halt instruction to see whether it is doing what it is supposed to do. Um, so at this point, pointer SP is going to be pointing to the last item. And what we want to do, okay, so let me go back to here. So what we want to do is pointer SP is now pointing back to location. Is now pointer SP points to this location. So that means the last element of the array is going to change to its own value because it has a null pointer. Okay, so you're good. Okay. Um, so in our code, okay, so let me save this and we'll run it. The nice thing about putting a halt instruction like this is it's easy to find the last thing that we need to check because you just scroll all the way down from the trace and basically the last update is what we need. So this is correct because the last structure in R starts at location 10. So this is the third location, which is also where we find member S. Member S is supposed to initialize to just its own value, the value of its own of the own structure when the next pointer is null, and that's exactly what it has done. So far, miraculously, I did not make a mistake. Yes, it is actually miraculous because I mean, you guys saved me a few times. Okay, so that's good. Um, and that's encouraging. Okay, so we can now take out the halt instruction because I think the loop is ready to go. And that's the last thing that we need to do in this program. So I think we can just let the program go. What do you guys think? All right, let it rip. Okay, so let's do that. We go back to here, just let her go. Well, it'd be fun if it is an infinite loop because then I can show you guys how to debug the program. Unfortunately, it does not seem to be an infinite loop. So what do you do when it is an infinite loop? You have to find out why the exit condition is always true. Okay, because that's why you're getting into an infinite loop. So why is it not changing? So you have to backtrack and kind of analyze it from that perspective. All right, so we're almost done. Okay, I know you guys are a little bit impatient. So the next location that should be changed is going to be 3 bytes below this, which is uh, 0f. So 0f should be a 9 plus 11, which is a 1, 4. So let's go check it out. Yep, 0sf is 1, 4. And then 3 bytes below that is a 0c. 0c should be 40 in decimal or 28 in hexadecimal. So let's go check it out. Do, 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 do. Aha. So 0c is indeed 28. And then the program should conclude very shortly. And then we go back to the entry code, and then we get to the only halt instruction left in the program. So the whole thing works. Okay. All right. Well, since I teach this class, I should be able to get this done. Okay, I did make a few mistakes along the way, and you guys helped debug the program because I'm glad that you guys, or at least some of you, are able to track the registers. which one has what. We cannot reuse this register because we're gonna use it later, because that's telling me that you're really getting it. Okay. So let me give you the access code to the lab today, which is not a whole lot, as I said, but you can use the lab time to get started with the homework assignment, which is actually easier than this one in some way. There's always a little catch, right? In some way, your homework assignment is easier, but yeah. All right. So node, that's it. So the access code is node. I'll see you all in the lab.